Alright, so now that we're pretty comfortable with limits, what we're going to do is we're going to take a very, very important limit called the derivative. So if you remember back to the video at the start of class, which talked about what calculus is about, we had one of these questions, and the question is the speed question. So you're driving, and your speedometer's broken. How on earth could you find your speed using your odometer? And so in the lower left-hand corner you see I have a graph of time versus distance. Right? So you maybe have a passenger and he's keeping track of the time, and at certain times he's telling you what mile marker you've passed. Right? And so if you're at mile marker 20 when you start, and then a half hour later he says that you're at mile marker 58, what would your average speed be? Well, we know how to compute the average. The average is how far we went divided by how long it took us to go there. And so we would just take mile 58 minus mile 20, and that's how far we went, and divide by the half hour. And our average speed would be 72 miles an hour. So, although that's a pretty good estimate, we probably want to figure out ways of having better ones. So, here, your friend is a little bit more responsible and tells you how far you've gone every 10 minutes. And so there's mile marker 20 and mile marker 58, and we've broken this into 10-minute increments. And so you go 18 miles in the first 10 minutes, you go another 12 miles in the next 10, and you go another 8 miles in the next 10. And so I'm going to take the average, and so average 30, what average 30 means is what's my average for the first 30 minutes. And so it's going to be 58 minus 20 over a half, which is 76, just like before. And average 20 is the average over the first 20 minutes. So I'm making the average slower, I'm making the average over a shorter period of time. And so here we take 50 and subtract 20, which is 30, and divide by a third, and the reason we divide by a third is 20 minutes is a third of an hour, and that gets us to 90 miles an hour. And then my 10-minute average, average 10, is going to be 38 minus 20, which is 18 miles, and divided by 1/6, because 10 minutes is a sixth of an hour, and so we get 108 miles an hour. Right? So our average for the half hour was only 76 miles an hour, but we notice that as we're closing in on shorter and shorter time periods, our first 10 minutes, our average speed was actually 108 miles an hour. And so as you shrink the amount of time you're looking over, you get a more and more accurate picture of what's happening at a specific time. So if we could do 5 minutes instead of 10, or if we could do 2 minutes instead of 5, or 1 minute instead of 2, or 5 seconds, or 1 second, every time we shorten the amount of time we need to look at, we can actually get a better and better picture of our speed at that moment. And so if I had a graph, how would I describe what's happening? So over there on the left is my graph. And let's add to it a couple of points. One point represents my starting time. So in the example of what we were just doing, the left point would be time 0. And the right point would represent time 30 minutes or 20 minutes or whatever. And then the y values represent what distance I've gone at that time. And so the slope of that line is actually the average speed over that time. And so what we see happening to our left are we have 2 points and a line between them. The line has a name. It's called the secant line. And the slope of the line is equal to the average speed over the interval, right, over the x values that we're looking at. A tangent line is the limit of the secant line. So if we make those secant lines get closer and closer and closer, the tangent line is going to be the line going through the point on the left. And as we decrease the interval, the average becomes a better and better estimate of the actual speed at time t1, the left time. So let me just make a point about limits. If I take the limit as h goes to 0 of something, some function, the limit symbol only treats the letter beneath it as a variable. So only h is a variable if I take the limit as h goes to 0. If I take the limit as t goes to 0, only t is considered a variable. What that means is everything else is treated like a constant. And so here's an example. How do we take the limit as x goes to 3 of x times y? Well, our limit laws told us that we could just take the limit as x goes to 3 of x times the limit as x goes to 3 of y. Now we have a rule for the left one. The limit as x goes to 3 of x is 3. And the limit as x goes to 3 of a constant is the constant. And since y is not the variable, right, the limit is moving x around, since y is different than x, y is considered a constant. So we get 3 times y. One more example. This is very complicated looking, but if we take the limit as a goes to 2 of the fraction a squared plus ay over x, well, first off, the limit laws tell us we can break it into a fraction of 2 limits as long as both exist. And the top has some a's, so they're treated like the variable. And the bottom has none, so x is treated like a constant. And y up top is treated like a constant. If you go back and you work on your limits, you can see that what you're going to get is the top you're going to be able to plug in 2 for a, and the bottom you don't have to do anything. So we get 4 plus 2y divided by x. So let's define the derivative at a point. For a function, f of x, and a point a, we can define the derivative of f of x at a, which we call f prime of a, in the following way. F prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h if the limit exists. And the interpretation of f prime of a is that it's the instantaneous rate of change of f of x at x equals a. F prime of a is the same thing as the slope of the tangent line at a for f of x. And so we can use that formula to compute f prime for certain functions. So let's compute f prime of 1 for f of x equals x squared. Well, f prime of 1, according to our definition, is the limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. If we plug in 1 plus h for x squared, we get 1 plus h squared, and when we plug in 1, we get 1 squared. So the limit becomes the limit as h approaches 0 of 1 plus h squared minus 1 squared, all divided by h. Now we can square that, and we get 1 plus 2h plus h squared when we square 1 plus h. And so we rewrite this in the following way. It's the limit as h goes to 0 of 1 plus 2h plus h squared minus 1 over h. Our 1's cancel, and we get this expression. And you may notice that the top, everything has an h, so we pull out an h, and the limit is okay with us canceling those h's as long as h doesn't equal 0. And the limit never lets it equal 0, so we can cancel those h's, and we're left with the limit of 2 plus h as h goes to 0. Now what that means is that as h goes to 0, it's the limit of 2 plus the limit of h. And if you want, you can go ahead and just plug in h equals 0 for this. So that will be 2 plus 0, which is known as 2. Now, here's a graph of f of x equals x squared, and we want to see, what does it mean that f prime of 1 is 2? Well, if I draw a slope of the tangent line through the point 1, 1, then the tangent line has slope 2. So the derivative tells us the slope of the tangent line. So let's go ahead and compute one more. This is a little more complicated. What is f prime of 2 for f of x equals x cubed? Well, we use the definition. We see that f prime of 2 is the limit as h goes to 0 of f of 2 plus h minus f of 2, all divided by h. And we can go ahead and plug in 2 plus h for x cubed and 2 for x cubed and get the limit as h goes to 0 of 2 plus h cubed minus 2 cubed over h. And if we cube that out, we get the expression on the right. You'll notice that there's an 8 and a negative 8, which will cancel, and we'll get this expression. And the top, like before, has h's everywhere, so we can pull out a common h, and then, since h isn't 0, the limit doesn't let it be 0, we can in fact cancel the h's and get that expression, the limit as h goes to 0 of 12 plus 6h plus h squared. And as h goes to 0, 6h will go to 0, and h squared will go to 0, and so we get 12 plus 0 equals 12. So we can see here that f prime of 2 is 12. And that's it. So what I want you to do is I want you to practice computing the derivative for a series of functions in the homework. Go ahead and take the quizzes, and I'll see you in class.